Go. All right, real quickly, we got the limit as x goes to -5. First step, never not first, as I will say, direct substitution, right? If you plug in a -5 in the top, you get 0. And if you plug a -5 in the bottom, you get 0, right? Now, when we get 0 over 0, I'm going to write that in the top right-hand corner, okay? And is the answer then D and E? No. Some people, not in this class, but I was talking with Ms. Skurhawk about her calculus students this year, and they had also a quiz recently, and a lot of them were putting 0 over 0 equals D and E. 0 over 0 does equal D and E if you're talking about the what there? Not the limit value, but the function value, right? The graph, the function doesn't exist there. The function value doesn't exist there. The graph doesn't exist there. But for us, 0 over 0 right now means that the limit does exist, right? There's a hole. And if we could find the y value of the hole, we'll know the limit value. And the most primitive method we have for that right now without a calculator and sneaking up on it from left to right, like we did in the beginning, is to factor and divide out. I call that the Fado method. Factor and divide out. Fado, right? Pretty clever, I know, right? So, the first rule of factoring is to look for a common factor. There's nothing in common, so you either factor by skill, or you know for sure that x plus 5 is a factor of the top and bottom because that's what causes the 0. Right? We talked about that the other day. If a is a root, x minus a is a factor. And then that can help you factor what's left. That should be a plus 3. Check the inner and outer, you get 8. And then x minus 3, check the inner and outer, you get -2 or +2. Now, those divide out. Notice I'm working straight down. So do I have the limit intact still? Yes, as long as there's a variable, I need the limit intact. But once I get rid of the 0 over 0 now, I can go back to direct substitution. And once I plug in, that's where I don't need the limit. So -5 plus 3 all over -5 minus 3. If this is a free response question on a test, can I stop there? Yes, we got some medical terminology in the house. There you go. Yeah, you could stop there on a free response. Multiple choice, we got to keep going. -2 over -8, which simplifies to 1/4, right? So right now in this context, whatever that function, x squared plus 8x plus 15 over blah, 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 it has a hole at the ordered pair, -5, comma, 1/4, right? And it also has a vertical asymptote where? At x equals 3. Yeah. Now, here's another thing that I want to point out. 2 more things that I was thinking about when I was trying to go to sleep last night. You don't want to just call this function f of x, right? In other words, like, you don't want to just say now that f of -5 equals d and e, right? Or say f has a, right? Because we never named it f of x. So if you're going to name it f of x, you could name it one time off to the side. F of x equals this, you know. This is more like for like short answer or free response questions where we're going to be working with the function for more than one thing. If this were only the question you had at task, it would be disposable, you'd be moving on. But now that I've called it f of x, now I can refer to it as, you know, the limit as x goes to -5 of f of x. I could write that. And now I could say f has a hole at the point -5, comma 1/4. But just be careful. Don't refer, like, we use f of x generically for like any function, you know? So it's tempting just to start wanting to call everything f of x. But unless it's been clearly defined, just kind of avoid doing that. The other thing, which is unrelated to this problem, but if you have something that looks like that, let's just say we have x equals 3, and then y equals 5, and let's call this y equals 6. This is what type of discontinuity? Still a hole. You know where I'm going with this. This is a still a hole discontinuity, which is the same as a hole, which is the same as a removable point discontinuity. This is not a jump discontinuity, okay? Even though as you're graphing it from left to right, you know, which is the way we want to, you have to jump up there to that single point to make it. and then jump right back down to the same y value, this is not a jump in the sense that a jump is. A jump is where the two roads don't meet. We don't even care about the function value. You're jumping from one y value to another y value for more than just a single y value, right? It's for a whole stretch of them. This is still a hole. So if this graph is f, f has a hole at 3 comma what? 5. Good. And f of 3 equals what? 6. Good. So this is the case where the function value exists, it's 6, and the limit value exists, it's 5, but it's not continuous because 5 doesn't equal 6. And it's not a jump. Yeah.
And the domain would still be all real numbers.
In this case, if this were the graph and we assumed it went on forever, the domain would still be all real numbers. Yes. Okay. It's not continuous. Now, of course, if we were actually to look at the equation of a graph like this, it would be a piecewise function, right? Because we can have holes existing like in the warm-up, but to have them explicitly redefined to either fill in the hole, like we had an example in the warm-up where we just plug the hole right back up, or to redefine it somewhere else, it's got to be a piecewise function, okay? So the equation won't be like just defined by a single equation. All right, so those are the 2 points I was trying to make. I'll think of some more things to emphasize tonight while I'm trying to go to sleep, right? Anything else? Anyone think of something when you're trying to go to sleep last night and you're like, man, China.
I thought about Haribo gummy bears.
What?
Like the Haribo.
Oh, Haribo gummy bears. Yeah, like the funny commercial where they're all adults sitting around the executive table and they're talking like little kids. Yeah, that's funny. I was thinking like China, like the Beijing Olympics, which are going to happen in how many years? Next year? Yeah. Right, I know, but because we had them a year late, we're going to have more Olympics next year, but it's going to be the ones with like the sleet and the snow. The winter, that's what they call them. I knew that was the name. Yeah, the Winter Olympics. Okay, let's jump back up here to example. Did we do example 12? I let y'all start it. Let's go ahead and do it together. If f of x, and here we're defining a function to be this function to the left and right of 2, and x is not continuous at -1/2, and then it's k when x equals 2. What's the limit as x approaches -1/2 from the right? Okay, so if I'm looking at -1/2 from the right, which piece am I looking at, the top or the bottom piece? The top piece, right? Because -1/2 ain't 2. Now, I would like to have that factored, right? So I can look at the vertical asymptote, because again, this is a really good free response type question. More than likely at 2, not necessarily, but more than likely the top piece has a hole at 2, and we're going to be trying to plug it by defining k to plug the hole at c. But if I can get rid of the hole, then I'm left with an equation that I can still use for the top piece that is much simpler to use, right? I mean, I don't want to have to like guess if it's what type of infinity and then plug in like a -0.51 into the top piece. That's just like, ooh, -0.51 squared? No, thank you. So off to the side here, let's factor it. It looks like it's going to be x plus 3, x minus 2, and then x minus 2 times 2x. And here's where I kind of help myself. If I know that maybe -2 is one of the factors, because it starts with the 2 in the bottom, a leading coefficient that's not 1. Let's see, if I need a constant of -2, then this has to be a +1, right? And now if I check the middle term, -4, yeah, that works. Those divide out. So what's left, and notice I'm not calling this f of x, am I? I don't want to call it f of x because it's not f of x in its entirety. But what's cool is I can use this for f of x everywhere except at 2, right? Including to help me answer this question. So why is it not continuous at -1/2? Well, there's a what there? The vertical asymptote. Yeah, if you plug in a -1/2 at the bottom, you get 0. Or if you set 2x plus 1, the denominator factor equals 0, you get -1/2. So what's the safe answer on a free response? DNE, free response, safe answer. Multiple choice question, I know it's going to be some type of infinity. And now let's see, now I can plug in a number that's just to the left of negative 1/2, right? Like negative 1/8. Yeah, you could use, that would be to the right actually, right? Correct? I mean, yeah. So because I need to double it, I might choose something like negative 1, I don't know, negative 1, or how about negative 0.6? That'll work, negative 0.6. Negative 0.6 times 2, double negative 0.6, you get negative 1.2, right? Negative 1.2 plus 1 is negative, who cares? Good. And then negative 0.6 plus 3 is positive, who cares? Right? So now what's a positive divided by a negative? A negative. That's it. We're only interested in the sign. Okay? And notice I didn't have to do that, but if I would have left the x minus 2 factor inside there, it would have been a lot harder to come up with that negative number, because now I have to actually look at more things to figure out the value in the top and bottom. Okay, cool. So I know it's decreasing on the left-hand side towards infinity of negative 1/2. What would be the limit as x goes to 1? Which piece do I use, top or bottom piece? Top piece, right? And how do I find that limit? Plug it in, right? Just to kind of, to remind you, right? This function f of x has a non-removable vertical asymptote at negative 1/2. It's going to end up being continuous everywhere else. And remember, if a function is continuous at a point, we know that its limit value is the same as the function value, right? Three-step definition. And function values are easy to find. So the limit as x goes to 1 is the same as f of 1 in this case. And if I want to evaluate the function at 1, I'm going to go ahead and say f of 1 here. You don't have to write that. But f of 1 is just plugging in. Now I can plug a 1 into this piece here, or I can plug a 1 into that piece there. It doesn't matter. You're going to get the same result. I'm going to choose the smaller version, right? So 1 plus 3 is 4 over 2 plus 1 is 3. It's 4/3. Yeah. Okay. And then finally, kind of tying back into the warm-up from last week, what is the value of k? Well, you might forget, like, I don't know. K is it's a letter, right? What do you mean, what's the value? So you have to kind of go back and read the instructions. You're like, oh, the function's continuous everywhere except at negative 1/2. So it has to be continuous at 2. Oh, and now when x is 2, I need it to be k so that I plug the hole. So really, the value of k, I mean, you don't have to write this out either, but it'll help you when you come back to your notes. K is going to end up being the limit as x goes to 2 of x plus 3 over 2x plus 1. Or if you want to write it out with the factors still intact and then divide out, you can, either way, right? It's going to be the y value of the whole from the top piece. Well, we've already factored, we've already divided out. Let's just plug it in. What do you get? 2 plus 3 is 5 over 5, which is 1. Do your math homework. Now, the way I wrote this, notice I put k equals. So now if I'm going to keep evaluating it, working straight down, I do have to put the equal sign there because I chose to equate it left to right. But you wouldn't need to even show that work. If you just want to say k equals 1, boom. Yes, sir. In section A of this question, oh, crap. I approached it from the left, didn't I? Yeah. I wasn't even zoomed in. I think I said right, but I was approaching from the left. I even told you yours was to the right. Yeah, which was correct. Thank you. Yeah, I'm even wearing my readers today. Yeah, that's a plus sign for sure. I could do one of two things. I could either change this to a minus sign and be like, well, that's what I meant, right? Or I could just admit my mistake, and I'm glad you caught it. What would it be from the other side? That's why I was getting some funny looks, right? Thank you. Thank you so much for the courage to speak out. It should be positive infinity. Let's go back and plug in something to the right of negative 0.5, like negative 0.4. Yes. Negative 0.4 times 2 is negative 0.8. Plus 1 is positive. And then negative 0.4 plus 3 is positive. Positive over positive is positive. Seguro. Yes. All right. Thank you. Thank you. Yeah, I'll make careless mistakes all the time. Sometimes my mistakes are on purpose, and sometimes my mistakes are on accident. But never are they my fault. No, always. Yeah. Okay. All right. Thank you. Thank you. Yeah, that I'm recording this. So if we would have left it like that, posterity, like cavemen in the future would have unearthed this recording and been learning math incorrectly, right? Cavemen in the future when they find this recording. So now we fixed them, right? Hey, try fire. It's really cool, right? It'll lead to the internet. All right. So far, so good? All right. There's one last type of discontinuity, and it's not going to be on the AP exam. It's called an oscillation discontinuity, okay? If you look at the graph of sine of 1 over x, what value is not in the domain here? 0, right? Now notice 0 is not in the domain because 1 over x is undefined there, but it's sine of that number. So here's what the graph looks like. I gave it to you. It oscillates between 1 and -1 because that's the amplitude of sine. But as you get closer to 0, it starts to oscillate faster and faster and faster and faster. And then if you keep zooming in, you'll keep seeing the same behavior. You can zoom in indefinitely, and it just oscillates faster and faster and faster between -1 and 1. So what's going to happen is if you looked at it from both sides, it's not a jump because these things never stop oscillating. A jump would be like, okay, I'm tired. Are you tired? I'm tired. Okay, on the count of 3, stop. And now one's at like 1/2 and one's at a -1/2. Then that would be a jump. But they never get tired, right? They keep going back and forth between -1 and 1 faster and faster. It's not a vertical asymptote because they never go, they never do that, right? And then it's not a hole either because they never say on the count of 3, stop. Okay, oh, and they line up with each other. It doesn't do that. They continue to like bounce back and forth past each other faster and faster. And I've been teaching this problem for 23 years, and they've been still doing that all 23 years. And they were doing that since like 2 cavemen generations ago, still. And they'll be doing it when the future cavemen come to planet Earth. They get closer and closer, okay? So what do you notice about the graph in the neighborhood of 0? It's undefined. They oscillate faster and faster, okay? So F oscillates faster and faster. Let's throw betwixt in there. Throw a little Shakespearean flair. Betwixt y equals -1 and y equals +1. Okay. What is the limit as x goes to 0? Well, it does not exist. Yeah. And remember, the limit can fail to exist for any number of reasons. Yeah. Oscillates.
It's LLL.
Oh, that's ILL. Oscill. Oh, yeah, I got a little carried away with the L's. I do the same thing with banana. I know how to spell it. I just don't know when to stop. B-A-N-A-N-A-N-A. Oscillates. Thank you. All right. So the discontinuities you're required to know: vertical asymptote, hole, which is the only removable one, it's the only one we can fix, and a jump. Okay. Vertical asymptote and jump, we always say it's at x equals the x value, which you can also say for the hole, but we could do one better with the hole. If we find the y value of the hole, we can list it as a point. Okay. All right. So real quickly here to summarize, prior to this class, the function value is what y'all were primarily concerned with, which is basically putting blinders on to the left and to the right in the neighborhood of, and just saying, okay, can I plot a point there? That's the right one. But now the limit is like covering up that piece and looking at what's happening from left and right, okay? And now with all these funky functions, with all these discontinuities possibly, it's only when we peel back both sets of blinders and look at the full picture do we get kind of the actual representation, okay? So in this case, they don't have to necessarily be the same. Good. All right, perfect time. The last thing I want you to do, and I've always thought about leading with this because this is more of an intuitive understanding of a limit, but this is kind of what we did in pre-cal when y'all first learned the limit. Just being able to evaluate a limit from a graph. So this graph is all kind of broken up. It's called graphus interruptus, which is Latin for interrupted graph. Go ahead and fill out A through L and just pull the value straight off the graph. Because these are types of things you might have to do just as a question in of itself. You'll see in the next section we have to do this as well. So it's a good way to finish this section and a good segue into the next. I'm going to go ahead and do it as well, quietly. And don't look at my work until you've got all yours done. And then I'm going to like have to zoom in so I can see here. And we'll see if we get the same answers. If mine are wrong, I'll change them to yours. Okay? That's what I'm learning today. Yeah, thanks, Braden. Do your worksheet. I think these are right. The equation for a graph like this, by the way, would be one giant piecewise function. I mean, it would be defined by lots of things. Yeah, did I get one wrong? F. Okay, good, good. I like that there's some, oh, that's good. 5 from the left. 5 from the left. Oh, yeah. Boy, that's not 2. You know, a man that is broke, that is given $2, may feel like he has been given an infinity amount of dollars, right? For he is now rich. Yeah, but 2, yeah, it's a riddle. But 2 is not infinity. Yeah. I don't know what I was thinking. I don't know how, what value I was approaching. I think I was approaching 6 from the left. Yeah. I don't know. How about the others? Did we get the same on the others? Good. Any questions on any of these? These are pretty straightforward. It's a real intuitive. You're looking at the roads, and then you're looking at the dots. I will point out, like at -2, like on the second to last one, again, just because you see a vertical asymptote and then the graph on either side, there is a dot at -2, 2. So this would be explicitly defined, you know, by some piecewise definition to exist, right? But in a single defined function, like 1 over x squared at 0, the function will not exist, okay? All right, so that concludes section 1.1. You can now, if you want, yes. Did I do J wrong too? Let's see, J, 8 from both sides. It's the general limit at 8. it- we're approaching the open circle from both sides. Did I put 3? Yeah, okay, yeah. And then, so the function, yeah, okay. Yeah, any other questions on this? I'm pretty good at careless mistakes, I gotta admit. All right, if you're done, you can go ahead and submit your notes right now into Canvas and get that free 100, and then the worksheet will be due tomorrow at 9 a.m., okay? Go ahead then, and if you want, go to Corpy's World and download the notes for 1.2. I'm gonna do the same thing, but I'm also going to restart the video here. So 1.1, it's been real, it's been fun. It's been real fun too, yeah.